Welcome back. Today, we are going to be learning about waves, and we're going to do that by page walking through chapters 25 and 26. So to start, you will need to pull out your textbook, Conceptual Physics, nice light blue one, and you're going to open up to page 372. 372, it's the start of chapter 25. You will also need your science notebook. And go ahead and open up your science notebook to your next available page. I have it as 51, but you can make up whatever number you want. Whatever page number you're on is good. Okay, so let's start on page 372. On page 372, it starts by defining how we get a wave. A wave is some kind of vibration or some kind of back and forth movement. One way of representing that is using a pendulum. So a pendulum swings back and forth. Every time it swings from one side all the way over to the other side and then back, we would say that's one vibration, one back and forth, and we could represent that as one wave. All right. Now let's talk a little bit about a few of the details. So the period is the amount of time required to make one wave. So period would be a time. Then if I draw a picture of the wave length would be the distance from crest to crest on the wave. So from here to here, or from trough to trough, or from midpoint to the next midpoint going down. So it'd be like from here going down over to here going down, or midpoint going up to midpoint going up. In any case, has one full crest, one full trough is one wavelength. Another way of conceptualizing it is it would be the amount of space from here all the way over and then back again, right? It would be one wavelength. The amplitude of a wave is vertically from the midline. How far up or how far down does the wave go? All right, frequency is 1 over the period. So it is the number of waves per second. The period then is the inverse of the frequency, 1 over the frequency. That would be the number of waves. Frequency is waves per second, etc. And this should be a review. All right, we're now over on page 375, and we can keep on flipping to 376. So wave speed and wavelength on page 376, 377, we introduce the relationship between wave speed, frequency, and wavelength. And that relationship is that the wave speed is equal to the wavelength times the frequency, or the wavelength times the frequency equals the wave speed. This is the relationship that's going to relate everything with waves. So it's an important one. Then on 377, it talks about the speed of sound. It shows a little table where the speed of sound remains constant, but the frequency and the wavelength vary. So wave speed of sound in air, our textbook defines as 340 meters per second. It actually varies slightly depending on the temperature of the air and the density of the air, whether you're at sea level or not, but we're going to say it's ballpark 340 meters per second. That's around 760 miles per hour. Okay, flipping on again to page 378. We start talking about transverse and longitudinal waves. We have already defined those in your Physics Everything sheet, so we're good. All right, then we can start talking about interference. So we're going to do a little demonstration with interference in class when we do our waves lab. But I wanted to start by just kind of showing how interference works. So interference is when two waves are interacting with each other. And they can either add together or they can subtract from each other, which I guess is actually still adding, but in a negative direction. It's like definition of negative numbers. So this is on page 379. So I've given a couple examples. In the first example, this is going to be what we call constructive interference. So this is where it's going to add together. I have a wave with an amplitude of 1 meter. So it's 1 meter up and then 1 meter down, or -1 meters. And then I add that to another wave and it's in the same phase. So you notice that the bump at the beginning goes up, and in this one, the bump in the beginning goes up. So they're matching at the same up at the same time. So it has 1 meter up over here and it has 1 meter up over here. It has 1 meter down over here and it has 1 meter down over here. So when I add them together, it's like I'm laying them on top of each other. And I end up with a wave that is twice as high. It goes 2 meters up and then 2 meters down, because 1 plus 1 is 2. -1 plus -1 is -2. All right. We call that constructive interference because they're adding together or constructing on top of each other. So that would be perfect constructive interference, where they match perfectly in phase. Destructive interference is the opposite. So that's when they're half a wavelength out of phase. So my first example is the exact same. I've got a meter up and then a meter down. And then my next one, you can see it is flip-flopped. So first it goes down a meter and then it goes up a meter. So I've redrawn that one in little dotted lines here. The down part and the up part are exactly opposite of the first wave. So when I add them together, I would have a meter up and the meter down. That adds up to 0. Then I'd have a meter down and a meter up, and that adds up to 0. So what I'm left with is 0, 0, or just a flat line. And we call that destructive interference because it's reduced the wave to nothing. Okay? So when the waves are perfectly 1/2 wavelength out of phase, they've been shifted over by 1/2 of a wavelength. And the reason I say it's over by half of a wavelength is that if this was continuing, it would continue like that, right? There's that extra half wavelength in purple. So it's half of a wavelength out of phase, and so it's destructive. It has opposite crests and troughs. Okay, let's flip on to page 380. So 380, 381 also has some good diagrams of constructive and destructive interference. So far, we've been dealing all with waves just on a straight line, but waves actually take place in the real world, so they're 2 or even 3-dimensional. So when I look at a 3-dimensional set, what ends up happening is here I've got 2 little dots that are bumping in the water, right? And as you can see, you get areas where you get double high points, you get areas where you get double low points, and then you get areas that are just kind of like mixed. So these gray spokes that I'm going to highlight right here, that's a gray spoke right there, that's a gray spoke right there. Those are areas of destructive interference, right? Those destructive interference areas just kind of like middle everything out. The areas that have the black and white, those are extra high and extra low. So those would be constructive interference. And I've marked those in purple. So the constructive interference, and I could go through, and that's the constructive line right through there. That's the constructive, et cetera, et cetera. So these ones that have where it's adding up to each other. So this black mark plus this black mark ends up with a mark right there, right? These dark marks, that would be constructive in the positive direction. The white ones would be constructive in the negative direction. So those are extra low troughs. Okay. So it's just showing that it doesn't actually end up with like perfect setups like this, where you get like a perfect 0. You'd have areas of constructive, areas of destructive. So that would be like a loud spot or a quiet spot in the room based off of how speakers are set up. This is also how surround sound works. You sit in the areas of constructive interference if you have speakers set up around the room for you, and then there's like some center point where it's like, whoa, the noise is awesome here, type of thing. Okay, flipping on to page 382. On page 382, we introduce the Doppler effect. Okay, so the Doppler effect is the idea that waves can stack up or get more spread out if the source of the waves or the receiver of the waves is moving. So let's say if we have a bug and the bug is just sitting in a pool of water and it's not moving anywhere, the bug is going to be moving. It's moving its legs, right? And that's making some waves. So as the bug bobs up and down, it creates some waves. And the waves go out evenly in both directions. So the waves go out evenly to B, and they go out evenly towards A, right? So A and B both receive the waves at the same rate that the bug is creating the waves. But if the bug is swimming in one direction, now all of a sudden, as the bug makes the waves, it's swimming towards the wave it just made, and it's swimming away from the wave on the other side that it just made as well. So if A is still over here and B is over here, well, now the bug, the B, is going to receive the waves really fast. See how they're all like stacked up on top of each other? And A is going to receive the waves at a less frequent rate because the bug is further away every time it creates a wave. Now, what this actually means in practice is we hear this a lot for noises. Anytime you have a car driving towards you and then past you, or a siren coming towards you and then past you, you will hear a shift of pitch, right? So it'll go high-pitched and then low-pitched. High-pitched as it's coming towards you and the waves are stacking up, they're becoming more frequent. Lower-pitched as it goes past you and the waves spread out and they're hitting you as that less frequently as it goes away. So that's kind of like the race car noise that you might have made as a child, or I still make as an adult. The like you're pretending to drive and you go, meow. The is the car coming towards you. The meow is the car going past you because it's now the pitch is falling as the car gets further away and the waves are hitting you less frequently. So the pitch goes high pitch and then low pitch as the car goes past you and the pitch changes. Okay. All right. So we can do this with a little demonstration with some tennis balls. I'm going to see if I can make this work. All right. So here we are. I'm going to see right about there-ish. Okay. So I have a variety of tennis balls. There we go. 3 tennis balls. Like so. And I am going to start. How far can I go here? Here? Yeah, okay. So if I start here and I just stand in one place and throw balls at the wall, I'm going to try to throw them at a consistent rate, and you'll hear when they hit. Ready? Go. Okay, so they go like bump, bump, bump. Gotta pick up my balls again. All right, now if I'm going towards the wall as I'm throwing, you'll see that they end up hitting closer together. So I'm still going to throw them at the same rate, but they'll hit bump, bump, bump. Okay, here we go. So you heard, hopefully, that they went boom, boom, boom. Even though I was throwing at the same rate, they hit faster because I was moving closer every time I threw. Now, the opposite is also true. If I am moving away from the wall as I'm throwing, then they will hit further apart, even though I'm going to be moving. All right, so now this is going to be tricky because I'm going to try not to run into these walls. Here we go. Ready? Go. Oof. All right, so what you hopefully saw there was that as I move further away, the balls hit less frequently, even though I'm throwing them at the same rate. And that would work whether I was running towards the wall or if the wall was moving towards me, because in both cases, the relationship between us is changing. All right. So let's go back to our whiteboard and we'll pick back up. All right. So that is the Doppler effect. And you'd also see this if it's taken to an extreme in something called a bow wave. So we said that our bug was swimming in one direction, and that works as long as the bug never catches up with his own waves. But if the bug swims so fast that he actually catches up with his own waves and then goes faster like this, then the waves end up stacking up behind him, and that creates what's called a bow wave. You could also call this a wake. It's pretty popular if you go water skiing or wakeboarding because it makes a nice big bump behind your boat, and then you can like jump off the bump. Okay, so what's happening there is you're just using the waves that your boat is creating, but if your boat is traveling faster than the waves it's creating, the waves all stack up, and you end up with these big kind of like wake lines behind you. And you can see those right there, where the waves are all stacked up, and as they stack up against each other, you get an extra big wave. Now, this also happens with sound if something goes faster than the speed of sound, and we call that a sonic boom. So if an airplane is flying faster than the speed of sound, if it's flying faster than 760 miles per hour, the sound waves behind the airplane are going to stack up, and then when all the sound hits you at once, it's going to go boom. That's just a lot of noise. So this is an airplane, not a fish. It's flying through the air, and these little red lines are the sound waves stacking up behind it. And so you'd get a sonic boom if you are a person on the ground down here. The airplane goes past me, no noise, no noise, no noise. And then all of a sudden, the sonic boom hits, ba-boom, straight to the head. All right. So we're going to do some chapter 25 practice problems. But first, let's talk chapter 26. So we can keep rolling because chapter 26 is sound. All right. Actually, I'm going to pause here. You can hit your chapter 25 and then you can come back and watch chapter 26. So we're going to pause there and come back for chapter 26.